Hi everyone, this is Ranjit and I'm back with another short update about a very useful feature of our mesh class. Our mesh class has R-trees built into it as its members, and what that means is that the vertices and the faces of our mesh are stored in a spatial tree structure. And that allows us to very efficiently query the mesh for a subset of faces or a subset of vertices based on some condition. And this can be very useful in doing some computations and running some algorithms on the mesh. And I'll first walk you through the different ways we can query the mesh, and then we'll take a look at the code and talk about what this can be used for. I'm using the low polygon version of the Stanford Bunny mesh for this demo. And the first way you can query this mesh is to ask for all the faces that are either inside or intersecting with a given sphere. Here we define the sphere with a center and a radius. I can move the center around and I can also change the radius. And this C# script component is calling the geom_algolib function, which is implemented in C++. And what you see in green color in the viewport is the output of that C# script component, which is the result of our query. And as you can see, as I move the sphere around, the output is being updated in real time. The second way you can query this mesh is to ask for all the faces that either intersect with or are completely inside a given box. So here we define a box using 2 points. And as I move those points around, that updates the box, which in turn updates the results of our query. You can see that being updated in real time. The third way you can query this mesh is to ask for all the vertices that are within a sphere. And this is just like the first query, except instead of getting back the faces of the mesh, you get back the vertices of the mesh. The fourth way to query this mesh is to ask for all the vertices that are within a box. Once again, this is just like the second query, except instead of getting the mesh faces back, you get back just the vertices of the mesh. So if we take a quick look at the code behind this feature, the R-tree class template is at the core of this feature. It is a very shallow wrapper around the boost R-tree, which is in the boost geometry index namespace. And this class internally has the boost R-tree as its private member. And the insert function of this class just calls the insert function of the boost R-tree. And all the query functions just internally query the boost R-tree. So if this is such a shallow wrapper, what's the point? Why even have this wrapper? Why not just use the boost R-tree directly? The reason I am using this wrapper is because I wanted to have an R-tree that worked, at least from the outside, that worked with our data types instead of the data types provided by Boost. If we jump into the mesh.cpp file where we actually use this R-tree, you can see that we create a box3 instance. This is our query box, and we pass this instance directly to our mesh class function. And inside that function, we take that box instance and directly pass it to the R-tree function. And if we step into the R-tree function, this box3 instance gets converted into a boost box type using private helper functions. So at least from the outside, it looks like this R-tree is working with box3 as its type rather than the box type provided by Boost. And I'm not really doing a very detailed coverage of this code because it doesn't contain any real logic. It's just a dumb wrapper around the Boost R-tree. And I considered making like a proper tutorial on how to implement your own R-tree from scratch and then using that custom R-tree for the mesh class. But then I didn't want to get distracted and I didn't want to go off on a tangent making videos on topics other than mesh algorithms. So in order to keep making videos related to mesh, I decided to just, at least for now, use the boost R-tree. Maybe I'll come back to the topic of R-trees again at some point in the future and make videos on how to implement your own R-tree. But yeah, not now. And we're going to use this R-tree in lots of different algorithms. We're going to use this in mesh closest point, mesh line intersection, splitting a mesh with a plane, intersecting two meshes, mesh Boolean operations, the R tree is going to come in handy in all of these operations. I mean, it's not absolutely necessary to use the R tree to get these algorithms to work, but the R tree would help make these algorithms run a lot faster than they would otherwise. Yeah, with that, I'll conclude this video. As always, the link to the source code is in the description. Thanks for watching, and see you in the next one.